So section 10.3 is concerned with phase transitions and how they are influenced by intermolecular forces. So the first phase transition that we'll look at is evaporation. This is when a liquid particle enters the gas phase. So there are a few things to recognize. The first is that evaporation can only occur from the surface of a liquid. In order for a particle to be able to move into the gas phase, it must first come to the surface and then it can leave. The other thing to recognize is that it is the highest energy particles that will be evaporating. In order for the particle to leave the liquid phase and enter the gas phase, it has to be able to have enough energy to break all of the intermolecular forces that it's experiencing. So if it doesn't have enough energy, it will get pulled back into the bulk phase. So one of the consequences of this is that evaporation is going to occur faster at higher temperatures because more particles will have enough energy to escape the surface. So it's important to realize that evaporation will result in loss of the most energetic particles. So what that means is that this lowers the energy of the remaining liquid, right? That means that the average kinetic energy of the liquid is lowered as a result of evaporation, and as a result, the temperature of the liquid will decrease. And this is called evaporative cooling, and it's one of the mechanisms that our body uses to maintain its temperature. So as evaporation occurs, the remaining liquid will becomes lower and lower in energy. That is, it becomes colder. So a little bit of language that we should be familiar with is that the gas that exists above a liquid at a temperature less than the boiling point is referred to as the vapor. So so that's important. So if the bulk liquid is at a temperature lower than its boiling point, the gas that is above it is referred to as vapor rather than as gas. So one of the reasons for mentioning this is we're now going to talk about a concept called vapor pressure. So what we're going to be describing is a scenario where we put a liquid into a container and seal the container. So here is the initial level of the liquid. Now, as we wait, what will happen is that the volume of the liquid will decrease and the pressure of the vapor pressure, will go up. But eventually we'll reach a point where the level of the liquid no longer changes and the vapor pressure, it ceases to increase, it remains constant. So eventually we reach a state of what we call physical equilibrium, where particles are moving as quickly into the vapor phase as they are returning to the liquid. And that's why the pressure remains constant and the volume of the liquid remains constant. So I like to think of this physical equilibrium that exists in this scenario as kind of like a parking lot that is full. So you see the parking lot is completely full. The total number of parked cars doesn't change, but there's constantly people coming and going. And the reason that the total number of parked cars doesn't change is because as fast as people are leaving, new people are arriving. So that's how that works. So when we talk about vapor pressure, we're talking about the pressure that exists when a liquid has come into physical equilibrium with its vapor in a sealed container like we were describing. So that pressure is what we're calling the vapor pressure. So the pressure of the vapor, once this physical equilibrium has been established, is called the vapor pressure. So we put our liquid into a sealed container, wait for everything to settle down, and then measure the pressure. And that's the vapor pressure. So why is this important when we're thinking about intermolecular forces? Well, it's pretty simple. the vapor pressure of a liquid will decrease as the intermolecular forces increase. And why? Well, because it's just tougher for particles to leave the liquid and enter into the gas phase. Okay, it'd be nice to be able to kind of quantify this a little bit further. Something to kind of just be mindful of is that a substance is described as being volatile if it has a relatively high vapor pressure. So things with a high vapor pressure, things that are volatile, often have a kind of like, quite a smell to them, because there's like lots of vapor associated with them and your nose is picking up on that. So that's why, the substances that we would put into something like a perfume, we're going to pick things that are not only have a pleasant odor, but are also like quite volatile. So way back in the beginning of this section about evaporation, we mentioned that evaporation occurs from the surface of a liquid. And it's important to recognize that this means that evaporation will occur faster when surface area is increased, because there's just going to be like more particles that are at the surface. And you've probably noticed this, if you take a cup of water and leave it on the table overnight, it doesn't really evaporate very much. But if you was to take the same water and pour it out onto the table and radically increase its surface area, it'd probably evaporate in just a few hours. So you can kind of see this phenomenon for yourself, and you've probably noticed it. So we mentioned previously that the vapor pressure of a liquid will increase with temperature. Yeah, and we just said evaporation is going to be greater as the temperature goes up. So in this graph, what we have is a series of compounds. Some have fairly strong intermolecular forces and others have weaker intermolecular forces. And then we're plotting for each of these compounds the vapor pressure, in this case it's given in millimeters of mercury, against temperature. And we certainly see the trend of increasing vapor pressure as the temperature goes up. And one of the things that we can note immediately is that the dependence of the vapor pressure on temperature is not linear. Okay, so we can see that straight away, that there is a non-linear dependence of vapor pressure on temperature. The relationship, if you were to analyze these curves, you would find out is logarithmic. Okay, so the next thing that we kind of see when we look at this graph is that they've drawn a line at 760 millimeters of mercury, which is 1 atmosphere, if you remember that from chemistry 161, and then they've labeled that line the normal boiling point. So what the heck is this? So the normal boiling point is defined as the temperature at which the vapor pressure equals atmospheric pressure, or 760 torr. So in each case here, they've dropped a vertical line down, and so that we have the boiling point of each of these liquids. So the boiling point, in particular the normal boiling point, is the temperature at which the vapor pressure equals 1 atmosphere. Okay, so let's look at the molecules themselves. Some of these might be kind of very obvious to you, what's going on with the intermolecular forces. So bromine, 2 atoms of exactly the same type, so that must be nonpolar. While it's nonpolar, it's pretty heavy because bromine atoms have a mass of around about 80. So a bromine molecule is going to have a molar mass of about 160 grams per mole. So, we would expect that to have fairly strong dispersion forces. And so as a result, you put those two things together and it kind of comes out with a modest boiling point. So we've got a boiling point here, it looks like around about 40 degrees Celsius for bromine. Now, diethyl ether is nonpolar, just like bromine, but it has a lower molecular weight. So diethyl ether, because it has it only has weak dispersion forces between the particles, and it has a modest molecular weight, has a really low boiling point around about, I want to say around about 37 degrees Celsius. So, on a really hot day in somewhere like Phoenix, Arizona, it would be present as a gas. And diethyl ether for many years was used as an anesthetic. And it's good because, the person's going to get lots of fumes because it's highly volatile. Now, ethanol is sort of well known as being quite volatile. It has a characteristic smell. It smells like vodka because that's that's what you're mostly smelling if you were to smell vodka. Boiling point around about 70 degrees Celsius. It has a really pretty low molecular weight, but it has dipole-dipole interactions. In particular, it has hydrogen bonds that can form between the ethanol molecules. Same with water, has a boiling point of famously 100 degrees Celsius. It's a polar molecule, pretty weak dispersion forces, but strong hydrogen bonding between molecules. And so that's why it has an even greater boiling point than ethanol. Now, when we go to octane, it's really non-polar, so only dispersion forces here, but it's got a pretty high molecular weight, and so that blows out the boiling point, bringing us up around about 130 degrees Celsius. And then now finally, we go to ethylene glycol, commonly used as radiator coolant. It's got a decently high molecular weight. It's not super high, but it's got lots of hydrogen bonding going on, and then that blows out the boiling point to almost 200 degrees Celsius. So the take-home message here is that as intermolecular forces go up, so does boiling point. And then the other thing to note is that temperature and vapor pressure are not linearly related. They have some kind of more complicated relationship. So then that kind of begs the question, what is the mathematical relationship between vapor pressure and temperature? And we're going to have to somehow take into account the intermolecular forces when we explain this. So it works out that there is a linear relationship between the log of the vapor pressure of a liquid and the inverse of its temperature when the temperature is expressed in Kelvin. And this is a graph showing that here. So we have log of vapor pressure versus 1 on the temperature in Kelvin for a substance called pentane, which is a liquid hydrocarbon. So the exact relationship, it turns out, is this. Log of the vapor pressure is equal to the negative of the enthalpy of vaporization divided by the ideal gas constant multiplied by 1 on the temperature in Kelvin plus a constant. So that means that the slope of this line is equal to negative of the enthalpy of vaporization over R. And that's where the intermolecular forces come in, because the enthalpy of vaporization is the energy required to take 1 mole of a liquid and turn it into 1 mole of gas. So the stronger the intermolecular forces, the bigger the enthalpy of vaporization. So this accounts for those intermolecular forces. So this equation has a name. It's called the Clausius-Clapeyron equation. And just as we said, it's log P is equal to negative delta H on R multiplied by 1 on T plus a constant. Now, this form of the equation, it's cool and all, but, we kind of... it's sort of awkward to be working with, like, we've got this constant in there. Every gas is going to have a different constant. it would be nice if we could get that constant to disappear. And so one way of doing that is to rewrite the Clausius-Clapeyron equation, not as the equation of a line, what they call the slope-intercept form, but rather in what they call the two-point form of the equation. And that allows you to kind of get rid of that constant. So first thing we're going to do is we're going to reorganize this equation so that we have C by itself. And then we're going to rewrite the equation for two temperatures. So basically what I'm going to do is I'm going to note that log P plus delta H on R multiplied by 1 on T will be equal to C, because I'm just going to bring this whole term over to the left-hand side. Okay, so now what I'm going to do is I'm going to write this for two temperatures, T1 and T2. And both of these expressions will be equal to C. Okay, so this is where it gets interesting. What I'm going to do now is so as they're both equal to C, they're both equal to each other. So we can kind of just like get rid of the C, right? And we would have log of P at temperature 1 is equal to plus the enthalpy of vaporization on R multiplied by 1 on T1 is equal to log of the vapor pressure at T2 plus delta H on R multiplied by 1 on T2. So those two expressions are both equal to C and equal to each other. So now what we can do is bring all the pressure terms to one side and bring all the temperature terms to the other side, and we can kind of start simplifying. So the first thing that we're going to do is apply our log rule for subtraction of logs and simplify the left-hand side. And then we're going to recognize that we have this term here that we can pull out as a common factor, and that's what I've done there. So collecting like terms and applying the log rule for the subtraction of logs gives us what we call the two-point form of the Clausius-Clapeyron equation. And it achieved what we want. We got rid of the constant C, so now we can use the Clausius-Clapeyron equation without having to look up a constant for every gas. Okay, so how do we apply it? Well, this is a classic example. If we look at the Clausius-Clapeyron equation, we'll see that there are 1, 2, 3, 4, 5 variables. And so a typical problem will be that you'll be given 4 of the variables and have to solve for the missing one. There are a few things that we need to be a little bit mindful of as we do this. But the most important one that you're going to notice immediately is that to be consistent with the units that we are using for R, our temperatures must be given in Kelvin and our enthalpies must be given in joules. So let's have a look at it. This question says at a temperature of 126 degrees Celsius, N octane has a vapor pressure of 760 torr. So that is what we call the normal boiling point. Given that the enthalpy of vaporization equals 39.07 kilojoules per mole for N octane, what is its vapor pressure at 25 degrees Celsius? So the first thing is that 25 degrees Celsius is a lot cooler than 126. So whatever we solve for this pressure, it needs to be less than 760, doesn't it? It's probably going to be a lot less than 760 because we're 101 degrees cooler. So here's the Clausius-Clapeyron equation. We're going to put in what we know. So we're going to let our first temperature, our T1 be 126. So P1 is 760. When I put in the enthalpy of vaporization, I'm going to turn that into joules. And the reason for that is because R has units of joules in it. So for R to function correctly, we have to have the correct units there. And then it's worth noting what the units on R are. They're joules per mole per Kelvin, and that's a good reminder that our temperatures need to be in Kelvin. So you can see that I've converted my T2 and T1 here to Kelvin by adding 273.15. So now I kind of evaluate all of the right-hand side and I get this number close to 4. And then I need to get rid of the log. So I need to take the anti-log. So I'm going to do e to that number, e to 3.9888. And that gives me the value of 760 on x. And then obviously I can just solve for x there by a simple rearrangement. And sure enough, I got a number that was a lot smaller than 760. So the question becomes, is there kind of an easier way of doing this? There was kind of quite a little bit of algebra in here. And the good news is, yes, it is. Yes, there is. So I'm just going to clear all of this stuff off. There we go. And then I'm going to escape the slideshow. So I'm going to fire up my calculator. And what I'm going to do is you'll find that most calculators will have what's called a solver feature. And what that means is that you can put an equation, say, like this one, into your calculator and then just hit the solve button and it'll tell you what x is. So I'll show you how that works on a Texas calculator. Yours might be a little bit different. But if you just YouTube solver and the model of your calculator, you'll probably be able to find a lot of examples of how to do this. So on the TI-84 color edition, like you can borrow from the library, if you go into the math menu and then you go up one, it'll take you to the solver. What you want to do then is put your equation in. So you see here where it says E1 and E2. What we're going to have is the left-hand side of our equation goes into E1 and the right-hand side goes into E2. And where we want x, we're going to use this button to insert x. So I'll show you what that looks like. So we're going to do log 760 on x. And then that's our left-hand side. And then now we're going to put in our right-hand side. So it's going to be 39.07 by 10 to the 3 divide 8.314 multiplied by 1 over parentheses 25 plus 273.15. Close those parentheses, minus 1 over parentheses 126 plus 273.15. You have to close a double lot of parentheses and we're done. So now you hit enter and it'll place the cursor on a line where it says x equals. And we don't have to give a value for x here. And then now we have to solve. So you can see that solve is written in green. And so we have to press the alpha key to access the green features. So now it's in alpha mode. When we hit enter, it'll solve. And there's our answer, 14.08, or to 3 digits, that's 14.1, just like we got when we did the algebra. So that's kind of nice. It just does all the algebra for you, and you can see that what we're solving for is displayed right there. Log 760 on x equals, etc., etc. So that's a real quick way of avoiding doing algebra and just speeding things up for these like solve for x type problems. Okay, I hope you found that helpful. We'll go back to the slideshow now. So a couple of things to keep in mind when you are using the class's Clapeyron equation. Your temperatures will need to be in Kelvin, but sometimes they're given to you in degrees Celsius. The enthalpy of vaporization needs to be given in joules per mole, but often in the problem, what you'll get is kilojoules per mole. Be cautious with the value of R that you use because there are several ways in which we use R in chemistry, but you need to use the value of 8.314 joules per mole per degree Kelvin. Now, P1 and P2 don't need to be in any particular units, but they must be the same units. So they either both need to be torr, or they both need to be atmospheres, or some other unit of pressure, but whatever you use, they have to be the same. And as long as you follow those guidelines, it'll it'll go pretty smoothly for you, especially if you use the solver. Okay, so the enthalpy of vaporization represents the energy that's required to go from a liquid to a gas. And that's an endothermic process. You have to put heat in to make it happen. And that's because we're breaking intermolecular forces. The enthalpy of fusion describes melting when a solid becomes a liquid, and you guys have probably observed that if you want to turn a solid into a liquid and melt it, again, it's going to be heat in. Now, if we have a gas and we want to turn it into a liquid, well, we have to cool it down. We have to take heat out. So condensation is an exothermic process. And similarly, if we have a liquid and we want to turn it into a solid, then we have to cool it down, don't we? We have to take heat out. So freezing is an exothermic process. So what we're really saying is that a process that is exothermic in one direction is endothermic in the other. The amount of energy that we have to put in to evaporate 1 mole of something is the same as the amount of energy that is released when we condense 1 mole of something. The energy that we have to put in when we melt 1 mole of a substance is the same as the energy that is released when we freeze 1 mole of a substance. So the sizes of the energy changes for a particular phase change are constant, but depending on the direction we're going, it might be exothermic or it might be endothermic. So it's worth reviewing some of the common enthalpy names. So the enthalpy or heat of fusion is the enthalpy change that accompanies 1 mole of melting something. And again, this is always going to be a positive number because you have to put heat in order to melt something. This one's a little bit confusing because fusion makes you think that things are becoming more solidified. They're becoming kind of like, closer together, more aggregated, but we're actually talking about the energy that is required to melt something. The enthalpy of vaporization basically represents how difficult it is to overcome the intermolecular forces that are needed to be overcome in order for something to evaporate. And it is defined as the enthalpy change that accompanies the evaporation of 1 mole of a substance. So taking 1 mole of liquid and turning it into 1 mole of a gas. And again, just thinking about this is going to be an energy in process. So we would expect that enthalpies of vaporization are always going to be endothermic. You have to put heat in order to evaporate something. The enthalpy of sublimation is going to become a little bit important later on when we talk about what's called phase diagrams, and that's the enthalpy change that accompanies the sublimation of 1 mole of a substance. So sublimation is when we go directly from the solid state to the gaseous state without going through the liquid. And a substance that is well known for doing this is carbon dioxide. If you have a block of solid carbon dioxide and you leave it on the counter at room temperature, the counter won't get wet, but the carbon dioxide will disappear because it goes directly into the gaseous form without going through the liquid. Now, sublimation is an energy in process because we have to break intermolecular forces in order for it to occur. So it will have the enthalpy of sublimation will have a positive value. So phase changes, as we've seen, are associated with enthalpy changes. If an enthalpy change is exothermic in one direction, when you go in the other direction, it will be endothermic. So condensation is where a vapor becomes a liquid, and this is exothermic. So energy is released when this happens. Okay, so when a gas becomes a liquid, energy is released. And so some people say that they swear that it gets a little bit warmer when it starts raining, and the reasoning that they're saying there is because, you know, the water vapor in clouds is becoming a liquid and that releases heat into the atmosphere. I'm not certain that that is a true phenomena at all. Freezing, which is when a liquid becomes a solid, is also exothermic because we're forming bonds, and bond forming is an exothermic process, and it has in this case, the enthalpy of forming a solid for water is negative 6.02 kilojoules per mole. Now, if we go in the other direction, i.e. evaporation and melting, then these enthalpy changes have the same size, have the same magnitude, but they'll have an opposite sign. So when we want to take 1 mole of a liquid or 1 mole of liquid water and turn it into 1 mole of steam, we have to put in 40.7 kilojoules, and the same for when we want to take 1 mole of solid water and turn it into 1 mole of liquid water, we have to put in 6.02 kilojoules per mole. All right, so we've mentioned this quite a bit. Sublimation is the process in which a solid undergoes a phase change to the vapor phase without going through the liquid phase. So classic example is carbon dioxide, and this process will be endothermic. It'll have a positive enthalpy change because we have to break apart intermolecular forces, and that requires energy. So one way that people will study the energetics of phase changes is using what they call heating or cooling curves. And so what we've got here is someone has measured the temperature of water as heat is added, and they've also kind of kept track of what phases are present. So in this case, what we do is we start at minus 40 degrees Celsius, where the water is very much solid, and so all the water molecules are in a nice orderly array here. And then we start adding heat, and we observe that the temperature rises linearly. And the relationship between the temperature rise and the heat that is added is that Q equals mc delta T. So that first step there of heating up solid ice, continues until we get to the melting point. And then what happens at the melting point is quite interesting. As we add heat and we start to melt our substance, we observe that phase changes occur at constant temperature. So even though we're adding heat, the temperature doesn't move beyond 0 degrees Celsius. Now, once we've melted 100% of our sample, the temperature starts to rise linearly again, and we find that the temperature rises according to the MCAT expression, so Q equals mc delta T, but our heat capacity is a different number now. So that's kind of interesting. And then when we get to 100 degrees Celsius, our sample starts boiling and it starts getting turned into a gas, but the temperature remains constant once again until the entire sample has been evaporated, at which point the temperature starts to rise. It rises linearly as heat is added, again, according to the MCAT equation, but we have a different C yet again. So yeah, so it's kind of interesting, right? But the cool thing is to note here is that the phase changes occur at constant temperature. So we'll kind of like zoom in on this process and kind of like go through it nice and slowly over the next couple of slides. So we're going to start at minus 40 degrees Celsius, right? And we're going to add heat. And what we see is we get a linear rise in temperature, right? And the nature of the slope of that rise is determined by the MCAT equation. So if you remember, this is Q is equal to mass, that's what the M is for, times the heat capacity times the change in temperature, the delta T, right? So it kind of makes sense. The bigger heavier our sample, the more heat it takes to change its temperature. So that's what we're going to see until we get up to 0, which is when the phase change starts occurring, right? Once we get to 0, it starts melting. So once we get to the melting point, what happens now is that molecules start moving, the most energetic molecules start moving into a liquid phase, right? Okay, and while this is occurring, the temperature remains constant. And it remains constant until 100% of our sample has been melted. And the energy that is required to melt our sample is determined by the number of moles that we have. That's what the N there stands for, and the enthalpy of fusion, and which is expressed in terms of per mole. So that's going to determine how much energy it takes to melt our sample, how much heat we have to add. So then what happens once we get to having 100% of our sample melted is when we add heat, the temperature starts to rise again. So once we've melted our sample, when we add heat, the temperature starts to rise linearly until we get to the boiling point, and the rise in temperature is again described by the MCAT equation. It's important to realize, though, that the heat capacity of the solid does not normally equal the heat capacity of the liquid. Okay, and that is definitely true for water. In fact, I don't know of any substances where that is not true. Now, once we've added enough heat, what's going to happen is we're going to hit the boiling point and the sample will begin to boil. So, at the boiling point, what's going to happen is as we add heat, the most energetic particle is going to leave the liquid state and go into the gaseous state, but the temperature will remain constant, right? And so, yeah, that's going to just kind of like stay constant until we turn 100% of our sample into a gas. Now, the energy required to boil our substance depends on two things: the size of our sample, how many moles we have, and the enthalpy of vaporization, which is the heat required to vaporize 1 mole. So that's how we can figure out the energy that we need to evaporate our object. Okay, so once everything is in the gas phase and we continue to add heat, what happens is now the temperature starts going up again and it starts rising linearly according to the MCAT equation. So once all the sample is evaporated, if you add heat, the temperature once again starts rising linearly according to the MCAT equation. But it should be noted that the heat capacity of the gas will be different from the heat capacity of the solid, which will normally be different from the heat capacity of the liquid. So we have to be a little bit careful when we look these heat capacities up. So if we wanted to, we could calculate using tabulated values the energy that's required to go from minus 40, say, to 130 degrees Celsius here for a sample of water or for any other substance. And it could be a little awkward because we'd have to add together a total of 5 different energy changes. So they do have problems like this, but normally we'll just be going across a span of temperatures wide enough that you wouldn't need to do, say, more than like 3 components. That's I've never seen one where they make you do 5. So typically I'm thinking they're going to make you do 2 or 3 steps on a heating or cooling curve. Because while we've got heat added here, we could also just use it to determine the heat that is released when a sample cools down as well. So here's a classic example. It says how much thermal energy must be transferred to heat 1 gram of ice at a temperature of minus 18 degrees Celsius until it is a liquid at a temperature of 25 degrees Celsius. So what I always like to do is to kind of sketch out a little heating and cooling curve and make sure I know what is going on. So we're going to heat something from minus 18 up to 25. So we're going to be starting with a solid in here, and we're going to be ending with a liquid out here. So you can see that what we're going to have to do is 2 MCATs and an N delta H, right? So we're going to have to calculate 3 lots of heat and then add those heats together. So it's going to look like this. We're going to do an MCAT, and then that's going to get us to where melting begins to occur. And then we're going to have to do an N delta H fusion, and that's going to get us to melting being completed. And then we have to heat our liquid from 0 up to 25. So we're going to do another MCAT. So we do have the grams of ice, but you can see that for our melting section, we're going to need the number of moles. So the first thing that I would do is go ahead and calculate the number of moles. And so we've just done that by calculating mass over molar mass. So this is how many moles of water we have. The next thing is we want to figure out how much we're changing the temperature of the solid by. And so we're going from minus 18 up to 0. So that's going to be an increase of 18 degrees Celsius. And then we want to figure out how much we're changing the temperature of the liquid by. And we're going to go from 0 up to 25. So obviously that's going to be a rise of 25 degrees Celsius. So now we're going to have to look up some constants. We're going to need the heat capacity of our solid, the heat capacity of our liquid, and the enthalpy of fusion of water. So once we've got all of that, now we can plug everything in to our equation. So we're going to do our 2 MCATs. Making sure we use the correct rise in temperature and the correct heat capacity. The mass is the same, of course, 1 gram. And then we're doing our N delta H in the middle there to account for the phase change from liquid to solid. So it's a little bit of work, and there's not really any way of speeding it up. You just have to be slow and cautious. Okay, so that concludes the video for section 10.3.